Good afternoon. My name is Grace Jang, and I'm here to talk about how ketamine produces a long-lasting enhancement of neuronal excitability. I worked on this project with my PI, Dr. Bruce McIver from Stanford University. Ketamine is a dissociative anesthetic that has been recently identified to produce antidepressant effects. Ketamine is best known for its actions on NMDA receptors, but it has also been shown to act on a variety of other types of receptors and ion channels as well. Thus, the mechanisms of action behind ketamine's antidepressant effects are not well understood at this time. We use electrophysiology techniques to measure ketamine's effects on synaptic transmission at NMDA and GABA-mediated synapses. Here are preliminary results. At both antidepressant and anesthetic concentrations, ketamine produced an acute depression in population spike amplitudes during drug application. This effect was reversed upon washout, as resulting in an increase in population spike amplitudes that was sustained for the duration of washout, which was up to 2 hours. The mechanism of action behind ketamine's acute effects appears to be an increase in GABA-mediated inhibition. This is evident through an increase in the pair-pulse inhibition ratio, which is calculated as the amplitude of the first population spike divided by the amplitude of the second population spike. As you can see, during baseline, the pair-pulse inhibition ratio was about at 0.8, but this increased to almost 0.9 during ketamine application. Ketamine did not have much of an effect on field excitatory postsynaptic potentials. This indicates an increase in postsynaptic excitability rather than an increase in synaptic transmission. We also tested NMDA receptor antagonist AP5 to see if it can replicate the effects of ketamine. AP5 was able to replicate the acute effects of ketamine as evidenced by a decrease in population spike amplitudes during drug application, as well as an increase in population spike amplitudes initially during washout. However, the washout effect was not sustained long-term, with amplitudes returning back to baseline by about an hour and 50 minutes into washout. We also tested NMDA receptor ion channel blocker MK801. MK801 was able to reproduce both the acute and long-term effects of ketamine, as evidenced by a decrease in population spike amplitudes initially during drug application, as well as an increase in population spike amplitudes during washout, which is sustained for up to 2 hours. Since ketamine has also been shown to block potassium channels, we tested potassium channel blocker TEA on population spike amplitudes. As you can see from this slide, TEA produced a much more pronounced depression in population spike amplitudes during drug application than that produced by ketamine. However, TEA was able to produce an increase in population spike amplitudes during washout, similar to that produced by ketamine. This increase in population spike amplitudes was sustained for up to 2 hours to washout. Here's a summary bar graph comparing each experimental condition to its respective control. Statistical significance was assessed using the Wilcoxon rank test. In conclusion, ketamine produces an acute decrease in population spike amplitudes via increased GABA-mediated inhibition during drug application. Ketamine produces a rapid, long-lasting increase in population spike amplitudes during washout due to an increase in neuronal excitability produced by a postsynaptic mechanism. APV was able to replicate ketamine's acute effects, while TA was able to replicate ketamine's long-term effects. MK801 was able to replicate both ketamine's acute and long-term effects. The results indicate the involvement of NMDA receptor ion channel and potassium channel blocks in ketamine's long-lasting actions, and this could be related to the long-lasting antidepressant effects produced by ketamine. Thank you.